Okay, let's get started. So we're talking about differentiation, and the very last topic is will show up in a second. Was multiple differentiation, or repeated differentiation, better yet. So you can differentiate once, twice, for as long as it's possible. All the functions that we have seen, they're pretty much all infinitely many times differentiable. So you can keep differentiating non-stop. All the polynomials, exponential functions, sine, cosine. With other functions, there might be if there's a hole in the domain, that certainly you cannot do anything about those. But the rest of it, as long as everything works out, differentiation also can proceed on, okay, non-stop. Okay, so there are, however, well, first of all, we have to have some definitions here, and that is the differential function followed by twice differential function. Okay, so in other words, the derivative of that function is differentiable. So there's a hierarchy, and so differentiable, which simply means that f prime exists. Okay, number two, twice differentiable. Then its derivative of the derivative exists, so f prime prime, which is the same as f double prime, exists, and so on. So thrice differentiable, and so on. So f three times differentiable. F triple prime exists, and so on. And then there are whatever number you can think of is possible to have, and then at the end there is an end actually, and that's infinitely many times differentiable. Which means that this process doesn't stop. Like all of the examples that we have. Everything is pointwise, so it means that we only differentiate one point at a time. The definitions apply to those points. But at the same time, we could speak of function differentiable everywhere, or differential throughout its domain. All of these are okay concepts. So there is actually, this is not the complete hierarchy, so that's at infinity. Okay, there is a 0th item here on the list. What is it? There is one more item.
It's not differentiable?
No, that would be not necessarily. It is. I'm talking about continuity. So it's like the less restrictive condition. So differentiability is more restrictive than continuity. Remember? So so because there are functions, once again, that are continuous, not differential, absolute value again, and as we progress this way, we have less and less functions. Okay, so there will be, at every step, there will be a function that is continuous, not differentiable, differential but not twice differentiable, twice differentiable, not three times differential. So there will be less and less all those functions at every step. But this is an important hierarchy, which we utilize later. And so, as I said, every time you make it smaller and smaller. If you go backwards, it becomes bigger and bigger. And then, so outside of continuous functions, there is one more category of bigger than continuous functions. They're called integrable, but we just don't put that on the list. So the functions are, for the most part, well behaved. As you expect, you zoom in, and the function looks like a straight line. That's differentiability for you. Just one more example of a function that is continuous but not differentiable in the context of this hierarchy is this. So, well, sine function discontinuous. but then, well, actually discontinuous, and then this one is continuous but not differentiable. Okay, so that's an example that we have, examples that we have seen. The third example is tricky. Say I could take to function that's differentiable but not twice differentiable. You can take x cubed. I'm sorry, x squared and negative x squared. If you make the graph of a function from two pieces of x squared, except the one of them on the left is upside down, then it is differentiable, but not twice differentiable. Okay, so you can certainly verify that with the first, so this 0, 1, and 2. The 0, 1 we studied why this is continuous. I hope it's clear. With this example 1, the absolute value function, you just look at the secant lines for the origin. They behave very simply. They either have slopes to the left, the slopes to the right, the slopes are 1, and to the left, the slopes are a negative 1. Okay, so that it means that you cannot possibly have the same limit. So you have limit of slopes from the left, limit of slopes from the right, and you know that it's going to be from the left it will be negative 1, from the right it's 1, so that's why it's not differentiable. Okay, so 1 not equal to negative 1. That's the differentiability. With the second one, you look at the derivative. The derivative does exist. So if I'm to compute the derivative of this function, so suppose this is f prime is well, it is, so f, well, let me write it out. F of x is equal to negative x squared if x is less than or equal to 0, and x squared if x is larger than 0. Okay, then I can produce from this, I can differentiate it piece by piece, and f prime of x is negative 2x if x is less than or equal to 0, and 2x if x is larger than 0. It includes 0. It includes 0, as you can see, differentiating this function, there is no trouble. If I try to the same plan as I did just with the last example, you can see what's happening to the slopes. What's happening to these slopes?
They're flattening out.
Flattening out. So what's the limit of the slope of these slopes?
0.
0. Okay. If I now look at from the right, from the left now, slopes, where do the slopes go?
0.
Also 0. So that's why it is differentiable. So this is okay. It works out just fine because the limits of secant lines will be the same from left and from the right, unlike the previous example. Okay. However, now we take this function, and what is so that's okay. The function is defined, and in fact the derivative that f prime is also continuous, as a matter of fact. Okay. The problem, however, is what is this function? Do you recognize this function? Negative 2x to the left and positive 2x to the right. Okay, how about I factor out 2? What's the function, this piecewise defined function, what is it?
Isn't it just a straight line with one slope at that point?
Well, let's take a look at it. To the right of 0, x positive, slope is 1. What's to the left? What? Negative 1. Okay, so once again, what is this function? The absolute value, the one that we just had. So indeed, this is simply twice the absolute value of x. This is our function, and we know, what do we know about this function? It's not differentiable. From the previous example, we just established that it's not differentiable, and so, well, we conclude then the function that we just built in example 2 is a function that is differentiable but not twice differentiable. Okay. All right. So there are more complicated examples of this kind, but this is pretty much tells the whole story. Now, the second derivative, as you remember, is important for whenever we talk about accelerations, and that is the primary cause why we want to study it. But there is another one, and that is the curvature. The curvature. So imagine you can detect. Well, what is the second derivative? Well, let's before we get to the curvature, what is the first derivative? The first derivative is, as a function, is a bunch of tangent lines. Okay, these are the tangent lines. Okay, on our curve. In the meantime, so that's f prime. The tangent lines is the f prime. So then, what is the second derivative? It is the f double prime is the rate of change of f prime. So in other words, f double prime is the rate of change of f prime. So in other words, how fast these lines turn. These tangent lines turn. Okay, so and you can compare. This one is fairly slowly changing the direction, or changing fairly slowly. Imagine that I have something like this, and during the same change of x, say, this is the value. You can compare how much more they have changed. So on the left, you can actually compare that the difference as far as x is concerned is about the same, right? So this is same, but consider in comparison how much it has turned in the former case versus the latter case. So the angle of the rate of change of the tangent line in the former case is, I don't know, not the rate, let's just say it may have turned by like 10 degrees or so. Okay, those green lines in the first example turn about 10 degrees or so. Okay, on the last example, how much they turn? They turn almost 90 degrees. And indeed, if you step out and they just use your idea of intuitive idea of the meaning of the curvature, you will realize look at those two curves. That one is not very curved. The second one is much more curvier. So this is higher curvature in the latter case. Okay, so that's for a later time of studying curvatures, but for the time being, we simply think of the second derivative as the rate of change of the first derivative. Okay, so and therefore the acceleration, therefore the rate of change of the velocity, which is the acceleration. So you can think of if you have as far as curvature is concerned, you can imagine that you have a straight path at first, straight part of the road, and then you won't see any. And you suppose that you have a tree here, okay, right here, a tree. Okay, yes, you're driving towards it. There won't be any. It will be right in front of you for a while, right? Because as long as you're driving on a straight road. As you start your turn, you pass that tree and start turning. What's going to happen to those trees? As you're turning, they will be doing this in front of you. They will be moving left, right, or right, left in this particular case. More trees turning So they are certainly, the trees themselves are just standing, but what you're seeing is they're turning in front of you right to left. And the more curvature, the faster they will be passing in your field of vision. So a field of vision, which is just another way of talking about tangent lines, except this time the tangent line is invisible. Technically, it is you're driving, and therefore, if you're driving, even if you're turning, your eye, well, actually, when you're turning, you tend to look that way where you're turning. But imagine that you're not. Maybe you're a passenger. A passenger might still look forward, straight forward with the car, with the headlights, and then the passenger will definitely notice how those trees are passing through the field of vision, and they can estimate the curvature of the road. Okay, so we already did a little bit of an example of plotting the curvature plotting the first derivative from the function, and you can certainly go backwards. But before we do that, let's do one more example, one more issue to address, and that's the tangent line itself. So the derivative is the slope of the tangent line at that point. Okay, so it's in other words a number. The slope is a number, which means that at that point, which means that we can find the actual line. So we have the point, we have the slope. So that's all it takes. Okay, that's uncomplicated. Why do we care? Remember, we started with those examples of where tangent lines come into play. It's either bouncing off like a curved pool table, and if you want to know where the ball will bounce off of a curve, then the only way to know is to actually find the tangent line through that point where it actually touches the side of the pool. So bouncing off, either just a bullet or a cannonball bouncing off a fortification or off any kind of object. So once again, if the object is curved, then you need to find the tangent line. In fact, just occurred to me, there is an example of more modern. It is the stealth technology, which requires the essence of the stealth technology. It deflects the radar signal away from the radar. So that's how radar works. It sends a signal, and when it comes back, it knows where you are. It detects you and then knows the distance. So if you can deflect it sideways, and then it doesn't come back as much, or at least as much, or not at all, it doesn't come back to the source, to the station, so the receiver, then that you impeding its effectiveness. And so then you have to deal with these things. And in fact, if you think about it, the problem, of course, is when you bounce it off, it might hit another part of your plane and then still go back to the radar. And it spreads out like this, especially if it's not smooth enough. It will actually disperse but not disappear. So you have to send it in a way as much to the side as possible so it will not come back to the enemy which is in front of you. In fact, you remember the two major American stealth planes are is it F-111 or something like that, and B-2 bomber. So that goes back to, and the first one, the night bomber, F-111, I think, it has this angular shape. Why? Angular shape in comparison to the B-2, which is very smooth. You remember those planes, maybe? Looking like this. This is F-111, looks like this a little bit. While B-2 looks like this. Well, by the way, it's much bigger. Why? Well, you can see it's much easier to figure out where the signal will be bouncing off if you have straight lines. So you don't have to deal with tangent lines or anything like that. Those the difficulties might be problematic. And they're just computational power, as far as I remember the story correctly. The computational power was not sufficient in, like, whatever, 1970s, where it was developed for the first time, in order to compute all the possible scenarios of the radar being deflected by something curved. So they went with straight edges, and so that they still fly that way. But B2 was developed in the 80s, and then their computers, I suppose, were stronger, and then they went with a curvy, more naturally aerodynamic shape, which is what you want from an airplane. And so, but they did do the tangent lines a lot there. Certainly, it's not exactly when you're developing it. You see, when it's all on the drawing board, before you can actually test it, you do have curves, just like we do. You might have y equal x squared at some point, and you, with the what we know, you can figure out where the signal will be bound, will be deflected. Okay, so anyway, so well, let's just take y equal x squared is our curve, and the question typically asks, find the tangent line to the curve at, say, x equal 2, x equal, okay, 2, doesn't matter. Not x equal 2 at a point corresponding to x equal 2, because the curve actually looks like this. So we are building a curve. We are building a straight line on the xy plane. So there's only one value of x here, and then that part might be incomplete. You need to find then the value of y, which is in this particular case x is equal to 2, and y will be equal to 4, right? So then this is the point of interest. Through this point, we're supposed to find the tangent line. How it works is no trouble, so we already know. So y equal x squared. So then y prime is equal to 2x, and in particular, slope at x equal 2 is 2 times 2 is equal to 4. So the slope of the secant line, which is still to be found, it looks like this. Slope is 4. Okay, and then what do you do? Use point slope form. Slope is 4, point is 2, 4, and then you just plug it in. So y minus the value of y is 4, the slope is 4, and x is 2. Okay, so that's your tangent line. Okay, so not to be confused with a common mistake is to take the 2x as your derivative, which it is. But you can only build the tangent line one point at a time, so the x has got to be specified. Otherwise, if I put instead of 4, I put 2x there, I'm in trouble. It's not going to be a straight line. Okay, so just watch out for that. Okay, so we have differentiation. We have those 4 rules. So I like assign 8 problems, so 9, slightly more than usual, for you to practice with for Friday. Practice differentiation. Not difficult when you have the formula in front of you. It should not be ultimately difficult, but depending on how comfortable you are with the calculus, with the algebra to begin with, because it's once again algebra of things. So applying those rules would be your homework. There is one more rule, but before we go there, maybe it is worth mentioning that we have the reverse problem. It's not worth it. I have been mentioning that many times, and that is the reverse problem, not from the function to its derivative, from derivative to the function it came from. Okay, so once again, it is position or location, velocity, acceleration, Okay, so the relation is simply the derivatives, and then so that's from the point of view of motion. This is the relation, and or f prime, f double prime. Okay, so that is direct problem. We know how to do it. With some practice, we can handle specific problems with ease, hopefully. The reverse problem is more challenging, and that is going backwards. So from acceleration to velocity, from velocity to position. But it is the reality of solving any kind of physics or engineering problems is that you know the setup, the acceleration is determined by the forces. Acceleration is determined by the forces, and then this is what you know. In the meantime, you might know the initial position, initial velocity, and with this information, forces plus mass plus velocity plus initial velocity, initial position, will give you your position at every moment of time, as we did with certain problems a few times. Okay. The only problem is so that is it is a challenging idea to understand. Thinking of differentiation as some kind of function that processes function and giving you a new function, and then reversing this direction of your computation to in order to find the opposite. So x squared prime is equal to 2x, and now if we reverse, this is what we write it like: integral 2x dx is equal to x squared plus a possible unknown unspecified constant. Okay, so this is the primary idea of solving problem with calculus when we have to move backwards. So this is one part. This is the second part. The first part is primary address in calculus 1. At the end we start part 2, and it continues on for a while in calculus 2. And so because it's easier, I suppose, to handle the problem once you are comfortable with differentiation, then you will be comfortable with what we call anti-differentiation. Anti-differentiation or integration. Okay, but really you cannot separate the two problems, and at least you have to have the reverse problem in your mind in order to understand the big picture. And solving problems, it's kind of obvious how to, if you know where you are at every moment of time, you can certainly find a lot about it, about how fast you're moving. So that is kind of not really a big challenge to begin with. It is the reverse, which is the really useful part of this, the more useful part of this theory. Okay. So we'll keep doing that. In the meantime, there is the third. What is it? Fifth. There is a fifth operation, and therefore there is the fifth rule of differentiation. So let's review compositions. They become more and more important as you progress to more advanced things. So compositions, informally you can interpret them as substitutions. Well, compositions of functions, which means that you substitute one function into another. So how do you combine or compose two functions? And then the answer is to substitute. So that's composition, is what's behind the word to compose, or composition is to substitute. Okay, so it's very, very different from the rest of that we have seen, that you do the algebraic operation: addition, subtraction, multiplication, and division. This is substitution, so there is no composition of numbers. So this operation is only available for functions. And so that's why it doesn't come up a lot in any kind of pre-calculus course, because in those courses you're mostly dealing with numbers, and then functions handle numbers, that's all. But calculus, we study functions, and then we combine functions in a number of ways in addition to algebraic ways. Compositions is another. So once again, let me write it out. Composing them is the first things to remember, to learn. So say I have y equal well, so it's square root of x squared plus 1. Okay, well, let's do this one is to be decomposed. So decompose or represent it as a composition. So do you know how to decompose this one?
Wouldn't you just take the square root of each number and that would just be x plus 1?
Let's say it again. So I start with x. What do I do with it? So that is maybe indeed just start with composition before getting to the decomposition. So you got the process itself is substitution. How do you unsubstitute? Think about it. The end result, what we do is two functions, we substitute one into the other, and they were supposed to solve problem and learn how to solve problems. When you have a function and you have to figure out what has happened, you have to unsubstitute one function from the other. It's like trying to unstir coffee from your unstir cream from your coffee. So you put coffee in your cream in your coffee and you stirred it, and then you have to pull them apart again. Okay, so it just takes some time to learn how. Okay, so this is how it works. You say y is equal to square root of u is equal to x squared plus 1. Okay, so these are two functions. I did not intentionally name them because names are they are names of variables. There are 3 of them, and there are 2 functions. If you name the functions, that will just make things more complicated. So sometimes you choose to do so, but the early stage as this, it's probably easier to do this. So and then this is the substitution. So I don't know. So this is my coffee and this is my cream. So it is literally substitution. U is replaced with x squared plus 1, and of course the end result literally replace with substitution. You replace that expression with what you've got. So it will be square root of x squared plus 1. So, but that's algebraic interpretation. Algebraic interpretation is substitution, and that's how, if you are asked to find a formula for the composition, so this is the composition. Then this is how you do it. You substitute in the end. You don't even have to simplify it half of the time. But it is very important also to understand what is happening, what is the meaning of composition, and the idea is a consecutive computation. So consecutive computation means that you don't get to carry out the second function until you're done with the first. Okay? So if you have 2 functions and you do addition of the functions, you can say you have a function x squared plus 1 and the second one function x cubed minus 1. Okay, so these are 2 functions. I would add them eventually, but what I could do, I have 2 employees and I ask the first one to do the first function and the second do the second at the same time to speed things up. And then they bring it to me and I add the results together. Okay, so no problem with addition of functions. So the operation is addition. But if the composition, think about it, what am I supposed to do? I have 2 employees, but I don't know the outcome of the first function until outcome of this. I don't know what to plug into the second function before we're done with the first. Okay, so that's the problem with compositions. They have to be carried out consecutively. Wait a minute, consecutively. consecutively executed. Also think in terms of like a assembly line. So let me try to put it in the form of a sequence of events. It actually reads from right to left. So start with x, then you proceed to x squared plus 1. That is my new variable u. I compute x squared plus 1 and just rename it. Rename it to, in order to recycle it later. And then I compute square root of u. That's my y. So consecutive. I cannot split this job to be carried out simultaneously. So just like with assembly line, some things cannot. You have to put the engine in before you put the hood in, or something like that, right? So you cannot do that simultaneously. You cannot even sometimes cannot reverse the order. Also, we should not expect it. So with addition, the order also doesn't matter, but with composition does. Okay. So anyway, so these are the compositions. So once you have two functions, it's pure substitution to find the formula of the composition, but decomposing is more challenging, but also possible. So let me just do one example. It comes from experience with composition to begin with. So say I have how about how y is equal to sine cubic root of x. Once you see a lot of parentheses, that is probably an indication of you see parentheses, but you don't see algebraic operations such as multiplication or division or addition. So then it might be an indication that you're talking about compositions. So so how do I decompose this? Start over, please. U is what?
The cube root of x.
Cube root of x, okay.
And then y is sine of u.
Y is sine of u, yes. Okay, so it's not necessarily has to be that complicated. One more example is say y equal sine squared x minus 1 sine squared x plus 1. Okay, what should you choose u to be?
X minus 1 over x plus 1.
No, u. I think you were saying what y is. What should I substitute into the into anything into a fraction, I suppose, in order to get this function? You see the repetitiveness of numerator and denominator? Yeah? Well, you could, but think about sine squared x is a composition itself. Sine squared x is actually computed in two steps. Take sine first, then square. So that certainly is a fair, just similar to the previous example, as a matter of fact. So the trick is, and this is a more challenging example than the last, just pick sine x. And since it's repeated twice, then you don't have to compute it twice. You compute it only once and then substitute. That's the advantage. So what's the formula for u? I'm sorry, for y? Well, you sort of substitute backwards. Remember, sine x squared is simply sine squared x is the same as sine x squared. So sine squared x is, it will be u squared, right? U squared minus 1, u squared plus 1. Yeah. Okay. So it is there is some challenge there, certainly. Sometimes. So anyway, the compositions, we've seen examples of compositions. Just give me an example that brings us closer to differentiation. and that is composition of functions is where do appear. Remember I mentioned some change of variables, change of units. Another example really related to calculus, and that is the horizontal versus vertical motion. So you might have, it's like you have a map. You are about to go for a trip, and you have a map, okay, and you plotted your trip. Suppose it's a straight line, okay. So and then you also not plotted, but rather just decided on how fast you're going to be going different periods of time. So you have your function is u equal f of x time. So you decided where you're going to be at every moment of time. So you maybe put the marks here. So some slower, faster, or slower, faster, slower, and then maybe faster again. Okay, so that's your function. The x is time, f is location on the map. Okay, so that's how usually a trip, or maybe it's a hike. Probably better to think about it as a hike. And then what can happen is the second part of this study. You look at the elevation map. So if it is a hike, there might be hills there. So you might encounter like something, a terrain. Okay, so higher, lower. I mean, if you look at it from the sides, this might be your path that you're gonna follow. It might look like this. Okay, so in other words, the second one is the function, say g of u equal to say z. Well, let's call it y. Is the elevation at location u. Okay, so these are u's, and these are the elevations. So these two things exist apart from each other entirely. So the trip on a flat map, you drew the line, you drew the location at every point of time where you're going to be. That's the first function. The second function, you put this aside, the trip or the hike like chart, and then you bring in the elevation chart, which is typically just a piece of paper with drawn, like ISO. What's the word? ISO. Well, anyway, every line represents the exact same elevation. Okay, so that's what typically they look like. You can also see it on a map like Google Map. They usually they also have those curves. You might have seen this like. So on this straight line, all the elevation is 1,000, and here say 900. Okay, so and once you have your trip planned through this terrain, you're gonna know how fast you want to know how fast you have to climb. So the map itself is, as you can see, it's written there, is elevation as a function of the horizontal location. There is no time involved. But now if we bring in the first function in, then we know how fast horizontally we're moving, and now we want to know how fast we're going to be moving vertically. Okay, so the composition of these two, f followed by g of x, that's the composition. Remember the notation, right? The composition is the elevation as a function of time. So once again, one at a time. You're computing it consecutively. For every x, you find your horizontal location. Then you find based on that location, you'll find your elevation. Okay, that's how the composition comes about, and now what remains is just to learn how, especially from this example, we can learn how the derivatives of these two functions will be, of these two functions f and g, will give you the derivative of the composition. So say h of x. the elevation function. I'm sorry, elevation function as a function of x time, not as a function of position, a function of location, okay, as it was originally defined, but a function of time. Okay, and the answer is actually quite simple. We will multiply them. So what's the rate of change of the elevation over time. So that map on the second map doesn't help us because it gives us this the elevation as a function of location, but we want to know how fast we are going to be climbing. So it will depend on how fast we're moving through the terrain in a horizontal fashion. So and the answer is just multiply. So there are two functions, two derivatives, multiply them, and you have your the derivative of the composition, which kind of makes sense. So in other words, what I'm saying here is that h prime is equal to g prime times f prime, roughly. Not really the most complicated formula. As long as you understand compositions, you won't have trouble with it. Unfortunately, it is a very common problem not to understand compositions in the first place, and that's why having the trouble with the chain rule, which is what it's called. It has a special name. So for some reason it's not called the composition rule, it's called the chain rule, because their compositions are once again consecutive events. So let's confirm that this makes sense. So the rate of change, how fast we're climbing, per unit of time is proportional. Look at it. So how fast climb. Okay. How fast climb is the answer is well, it is proportional to how fast we're moving horizontally. That's what f prime is. How fast we're moving forward. Right? How fast we're moving forward, and so if we are think about it, if we increase our horizontal speed twice, double it, what's going to happen? We will have to climb twice as fast up. Right? It's the same road. It's the same road. If we're moving this way twice as fast, we will have to climb twice as fast as well. Okay? And then on the other hand, this one, the second one, it is what does it give you? This gives you the literal slope or steepness of the slope. Once again, I don't want to use the mathematical word in this setting. So steepness of the hill or of the mountain. Okay, so that's what G prime gives you. See, G is the elevation as depends on the location. So there are no travelers there. It is literally look at the picture and see if the slope is this. That's how I record my elevation, and then it's called the grade, right? I think it's what's called the grade. The how fast you have to climb per unit of horizontal progress. Okay, so and then once again, if steepness doubles, then you have to climb twice as fast. Okay, so that is the chain rule. It has to be stated in a more careful way in order to be careful. Let's carry out a simple computation. Suppose g of u is equal to, say, 3u plus 1. F of x is equal to 5x minus 2. Okay, so well, we will go with derivatives. G prime of u is equal to 3. F prime of x is equal to 5. Then the claim is that the composition, if I have g followed by f and differentiated with respect to x, the answer should be the product 3 times 5 or 15. Okay, we can certainly confirm it. When functions are simple enough, like this, we can confirm it how? By carrying out actual substitution, having a function of x, and then differentiating. So, okay, so let me substitute. So g circle f of x is equal to, here's the second way to write it, the composition. So the second one indicates, this is just the name, and on the right it is actual substitution. After all, what is f if not u? So this is u. So, okay, so then I have, let me do it one at a time, g, and then 5x minus 2. Okay, and now 5x minus 2, that is the u, so I'm replacing, in my formula for g, I'm replacing u with 5x minus 2, in parentheses preferably. So I'll have 3 5x minus 2 plus 1. So that is the actual composition. The only reason why I don't need the chain rule here is because both of the functions are linear. Most of the time, if you look at any of the examples we have seen, as the sine of a cubic root of x, you cannot decompose it into any other algebraic operations, only as compositions, and therefore for this one the chain rule is simply unavoidable. So anyway, and then we differentiate. So g circle f prime of x is 3 5x minus 2 plus 1 prime. I simplify, have 15x minus 6 plus 1. Well, the answer is 15. So yeah, it matches. Okay. All right. So let me state the chain rule. Okay. So once again, we have to be careful about differentiability. So suppose u equal f of x is differentiable at x equal a, and y equal, hold on, is it there in the right order? I want to do it the same. The f comes first, then g. Y equal g of u is differentiable at, well, where is it the other one should be differentiable? Y equal what?
U.
No, u is a variable. Okay, so but we're looking at one point at a time. So it is a particular u that we have to plug in. Not y. It is. I'm sorry. It's not y. I'm sorry. I'm only confusing you. This is supposed to be u. U equal to what? Well, what is the corresponding value of u? So we're going from x to u to y. This is f and this is g. And then I pick a particular value for x equal a. What's the corresponding value of u? F of u. Right? So the point is that we cannot assume that the function is differential everywhere, so we have to be careful about f of a, I'm sorry, f of a. Where is a taken by f? It's taken to f of a. Okay. Okay, then the composition, so which is y equal g circle f of x is differentiable at x equal a. It's a function of a, so we're fine. And then we have the formula. So I think I might need a name before it. Okay. And g circle f prime of x is equal to, not x, but rather we're talking about one particular value, so I have to put a here. So it is g prime of f of a times f prime of a. Okay, so it looks slightly more difficult than the original, but the plan is still still the same. You can actually have a verbal explanation so that you don't have to remember the whole thing. So the derivative of it depends on you, frankly. If you prefer formulas or you prefer words. So the derivative of the composition is the product of the derivatives. So that's the chain rule. So the composition turns into a product. So remember, the derivative of the sum is equal to the sum of the derivatives. The derivative of the difference is the difference of the derivatives. And this one is certainly not similar because composition turns into a product, sort of. You could interpret this as a composition, as a matter of fact. You could. It is not impossible to. I just don't want to go that in there. It's just take us off track. But it is. You can say it's composition. It is possible to interpret it this way. Okay, so it's not equal to the composition, and one reason why we reject that idea of the derivative of the composition is equal to the composition of the derivatives. The units don't match again. Remember the product rule, that discussion. Then we realize that it simply does not, cannot possibly work because the units don't match. So I just, you can have similar analysis here to see that you have to multiply those in order to have units to match. So another interpretation, you remember that the function f in particular might, if a different example from what we just saw for where compositions come from, might be, say, f is, so y is equal to g of x is once again location, x is time, but, y equal to g of u, and u is time, and then what is x? X is also time, but possibly measured in different units. So say u is time in minutes, and x is time in seconds. Okay, so you are scaling things. So you see where you develop a whole theory there, and then it seems that everything is dependent on the units that you choose. So if I change the units from minutes to seconds or whatever, then will still thing hold. And yeah, it does, because then if I'm switching and I'm trying to find out what my speed is, which is g prime of u naturally. This is my speed or velocity, g prime of u. But what if we switch from seconds to minutes? We have my f of x equal to, what is it? So if x is time in seconds and u is time in minutes, what is the function f? Converting one to the other.
Multiply by 60.
Divide. If it is time in seconds, divide. Yeah, happens all the time, unfortunately. X over 60, which means that, and then its derivative then, f prime of x will be 1/60th, and that is what will appear here in the chain rule. So once you are computing your speed, and now you're computing it in terms of seconds, it will go down by a factor of 60, right? So because per second you'll cover 1/60th of a distance. Okay, so that's another composition. So compositions are really ubiquitous. Okay, the second version of the chain rule is for the for Leibniz notation. So this Lagrange notation that you see at the top with primes. Now, what if I want to write it in the Leibniz notation? So I have from x to u, from u to y. Okay, so these are the three variables, and I'm throwing out, as I did yesterday, names of functions, and we'll be looking only at variables. Or alternatively, you can think of this as if that is the same name of the name of the function is the same as the output variable. Okay, so then this is what the derivative, what the kind of a complex formula turns into if I omit both the names of the functions and those parentheses for variables. So I'm looking at d dx, I'm looking at dy dx. Okay, so my variable y depends on x in 2 steps, or it depends directly. It doesn't matter. It doesn't matter. Y depends on y depends on u depends on x, which means y depends on x, which means that I can compute the rate of change of y with respect to x. We call it the derivative. We write dy dx. Okay? Now, the second term in my formula at the top, it is the derivative of the second function. So it is dy du. And multiplied by the derivative of the first function, which is du dx. Okay? This is all the chain rule, even though it looks quite a bit different. But once again, if you take the verbal description, it's not really that different. So the derivative of the composition, which is what you have on the left, is equal to the product of the derivatives. It is also nice how you can, do you see the pattern, how if you look at the right hand side and look at think of these as fractions. They are not fractions, but if they were, do you see how you can cancel things? You see it? That's the way to remember. So if you write these two, multiply them by itself, and the numerator and denominator in this metaphorical sense cancel, and then you have dy over dx on the right. Okay, so it's not really that hard to remember. So let me differentiate. Let me take and differentiate sine of cubic root of x. Okay, so say h of x is equal to sine cubic root of x. Okay, so none of the other rules will apply. You have to identify this. Just say right out, this is a composition. And then there is no way around it. You have to decompose. Because, you know, if it's a composition, you have to apply the chain rule. For the chain rule, you have to know the derivatives of the functions involved, and so you have to decompose. Okay, so you have to decompose. Okay, we already know how, so let me just write it out. I will write it once again using the variables. So I will write, I will introduce the new variable here, and I call it u. That is entirely up to you. I call it u, you can call it v or t, doesn't matter. Okay, and then so u is equal to introduce new and disposable variable, intermediate variable u equals cubic root of x. And then I do the decomposition, desubstitution step, and my variable say this is say y, so y is equal to sine u. And that's the decomposition. So you're done with decomposition, then you differentiate, right? So I'll have du dx is now, how do we differentiate cubic root? We talked about that yesterday.
1/3
X, yeah?
to the negative 2/3.
No. A root becomes the denominator. A negative appears when you have division. So what's the power? Power of when you have cubic root, what's the power of x? One third, and then you apply the product of power formula, and you have 1/3 x negative 1/3 minus 1. Okay, in other words, you have 1/3 x negative 2/3. Okay, and then you differentiate sine. That one is easy. Dy du is cosine u. Okay, now use chain rule. So my dy dx is the product of dy du times du dx. Okay, so where is my dy du is done over there, cosine u. Okay, and then times du dx, which is 1/3 x negative 2/3. So this is one, comes here, and the other one is here. Okay, the substitution is finished. What's not finished yet? There's one more step. What's the last step? Look at the formula. What?
To combine the two terms?
No, you cannot really combine them. Actually, I mean multiply how cosine multiplied by this thing. It's you cannot simplify it. Look at u. What's the significance of u?
To be disposable.
It is disposable, so it has to be disposed. It cannot be here. The answer has to be in terms of x. So how do we dispose of u? Plug in cubic root of x. Right. Just don't substitute by mistake the derivative. Happens all the time. So x negative 2/3, and then this is the answer. Okay, so so there is no chain rule in your homework yet. So next time. Okay, so so some examples you can look up for that purpose. Okay, I think we covered more or less the main things. Okay, well, yeah, there is more to the chain rule, so we're going to be talking about things that are related to the chain rule. Okay.